topic I spent many years researching. I left academia in 2006, but I kept an active interest in this, and I'm finally able to give the final answer. I also took the liberty of borrowing a subtitle from Asia. In my case, I not only appeased, but I was able to ultimately overcome the exponential inevitability. So, a bit of motivation. Why do we want to know this number? Well, as George Mallory responded when asked, why do you want to climb Mount Everest? Because it's there. This number is also out there. The most basic question about the game we all love. How many positions are there? Now, in popular press, you often see this expression of the number of goal positions. It's more than the number of atoms in the universe, which upsets me a little bit because it's a horrible understatement. In fact, it would be appropriate for the number of 13 by 13 positions, but it's even orders of magnitude less than the square root, the number of 19 by 19 positions. Another reason to compute this is because it's a huge computational challenge. And finally, it's the single major open problem left in our paper, combinatorics of so, by myself and Gunnar, that we actually presented, it was 2005, Computers and Games in Turin, Italy. So, without further ado, the number of legal compositions is number in all its 171-digit glory. And we can see, looking at the first 10 digits, that it exactly matches the estimate we were able to make 10 years ago. So, of course, the number of arbitrary n by n positions is 3 to the n by n. And in fact, there is a straightforward one-to-one correspondence with the numbers from 0 up to 3 to the n times n minus 1. Namely, we can write these numbers in ternary with n squared trits. And if we position those trits in an n by n square grid, then it's just a matter of translating 0 to empty, 1 to a black stone, 2 to a white stone, and you have all the positions. So what we can do is take the number of legal go positions and view it as a go position. Unfortunately, it's not legal. We have a black stone here surrounded by 4 whites and another one here. So today I can not only show you the number of legal go positions, I can let you feel the number. I was able to engrave this on a piece of plexiglass, and if you like, pass it around the room, everybody can get a feel of the number. So,
This is a number. Can you explain how that feels the number?
This is a number.
I don't understand what you mean by feel.
You can feel the engraving, because you can feel the ridges, right?
Oh,
it's cut into the plastic.
This is one position.
Oh, you put the number.
That is this position. Yeah.
Ah.
This is the number of go positions written in ternary. It's
a
a very special position. Unfortunately, it's illegal. I mean, it was bound to be. It was very likely to be illegal since only 1.2% of positions turns out to be legal. Actually, we move on to a bit of history now. So back in 1992, a certain Efrim Flammenkamp was using a simple sampling to estimate the number. So he was generating random 19 by 19 positions and then testing, is it legal, is it legal, is it legal? And that way he was already able to see that it's about 1.2% of all possible positions, yes?
Does the number of legal positions depend on the rules?
No, not at all. No. The variations in rule sets are only affecting what are legal moves and how to score a position. But the notion of every string having empty points adjacent to it, that's of course common among all rule
So
sets.
you can have all but once for every block, that would be legal?
Sure. Perfectly legal.
But how would black make so many moves without a white one?
White can pass in between.
Oh, okay, okay.
Yeah, that's one of the basic theorems in our paper, that any position which is legal is of course reachable in a legal game. So 2 years later, people wrote programs to compute these things by brute force, but then they were only able to get up to L45, which means the number of legal positions on a 4x5 board. This is already about 1.8 billion. So you can't go much further because it takes too long to enumerate all those positions. It wasn't until 2000 that someone by the pseudonym, I think, of Les Fables described the dynamic programming method, which which all this work is based on. That was not implemented until 5 years later by several people around the same time. But the first really correct implementation was by a gunner. This is what happens when your laptop is not hooked up to the power. Okay, we'll have more of these interruptions. So we got all the way up to there, and my contribution was to completely optimize the implementation, and that allowed me to go up to L to 13x13 boards. Later on I got help from Michal Kuczki, who is also at the Center of Mathematics and Computer Science in Amsterdam. He contributed some more ideas, particularly using a file-based implementation, because the computation was getting too big for my memory. And using the CWI computing cluster, we were able to get up to 17 by 17, so pretty close to the real size. But then we ran out of computing power. Over the course of this period, I asked many institutions and supercomputing places if they were willing to contribute computing power, but all such requests were turned down. Until recently, in 2014, a good old friend, Piet Hutt, at the Princeton Institute for Advanced Studies, said he would like to help out. And in fact, I started the 18 by 18 computation on a couple of machines at Princeton. And about 9 months, a good part of a year later, I was able to announce 18 by 18. That was announced in many places, Slashdot, Hacker News, and there I also made a plea for even more computing power to tackle the final problem. So forward step one, Michael Di Domenico, the system admin at the Princeton Institute for Defense Analysis. Pure coincidence that these places are both in Princeton, opposite sides. And he had available to him quite a bit more computing power, about double what I had available at the IAS. So then I started the combined effort, and that finished late 2015, but I didn't get the results in a usable form until early 2016. So then, the remainder of the talk is mostly about how do we compute this, the algorithm. So basically at the outer level we use something called the Chinese remainder theorem. If we're trying to determine some big number, we can actually compute it modulo many small numbers and then recompute the result. So the theorem says if you have a bunch of relatively prime numbers m1 through mk, then any number up to the product of them can be determined by the remainders, n modulo m1 through n modulo mk. And here's an example with two relatively prime numbers, 5 and 8. You see they don't need to be prime. And if you take the numbers up to 40, so 0 is 0 mod 5, 0 mod 8, 1, 2, 3, 4, 5. You can see that all the first 40 numbers take up unique slots in this table. So if we know some number n is 4 modulo 8 and 3 modulo 5, we can just look up, okay, 4, 3 must be 28. Another property you can see here is that one of the results is off by a little. Let's say modulo 8 we got 3 as well. Then you get an answer that is completely different. So this actually gives us some built-in error detection for our result. If any of our modular computations gives the wrong result, then the final reconstructed answer will be completely wrong. This gives us confidence that the result is correct. So then the outer loop is as follows. We pick 9 different offsets, and we're going to compute number of 19 by 19 positions modulo 2 to the 64 minus d. Of course, 2 to the 64 is nice because it fits nicely in a machine word, and we can compute very efficiently with that. Here you see where the different computations took place. Each of these is a multi-month computation. So I started myself number 0 at the Institute for Advanced Studies. This was the first to be completed, and it was announced separately, in fact, because computing modulo 2 to the 64 also allows you to state the final 16 hexadecimal digits. I let Michael take care of the next 6 available offsets. Of course, making sure that these numbers are relatively prime. Basically, we were computing about 3 at the same time. So it took 3 months, then another 3 months, then another 3 months. There were some hiccups, some disasters, files becoming corrupt. But in the end, we got the required remainders, 9 of them. So that gives us basically 9 times 64 bits is 576 of precision. And knowing that the answer takes 566 bits, that's enough. And then we can simply compute the result with a program implemented in Haskell. That's very good for multi-precision arithmetic. So then, how do we compute one of these modulo 64-bit number? Well, basically we count partial board positions. We count point by point. So we start with partial board of 0 points. Of course, there's just a unique position on 0 points. We consider all possible colors at this point, empty, white, or black. And then we obtain counts for partial positions of just 1 point, and then partial positions of just 2 points, all the way to the end. At each time we maintain 1 count for the illegal partial positions, which we cannot possibly extend into a legal position because we already have a string without liberties that cannot get any more. And then we'll maintain counts for classes of other positions. The dumb thing would be to have a count of 1 for every individual partial position. Then you're basically back to brute force enumeration, and you will be exponential in n squared, which is terrible. But using dynamic programming, we can abstract away from the irrelevant details of the partial positions. So these positions all have in common that these are positions on the partial board of 5 points. They all have in common that the last 3 points are an empty point, the black stone with liberties, and the white stone with liberties. It doesn't matter that there are 2 more white stones here or 2 more liberties here. We're only concerned with, okay, how can we extend this partial position into a legal one? So what matters is only the state of these last n stones, what I call the border state. Similarly, these 4 positions are all represented by this one, namely they have an empty point, a black stone with liberties, a white stone without liberties. So we need to identify which stones do not have liberties, but also connections among them. So, for example, in this case, we need to say, okay, this is a stone without liberties, this one is without liberties, this one is a different white string without liberties, these are not connected. If these 2 white stones would have been connected, we need to record that fact. So that when extending the partial position, and we decide to put an empty point here, we can not only see that this white stone will have liberties as required, but it will also provide liberties to this one. So with this abstract representation, we can just consider all possible values of the next point, and then update the state. And also detect when things become illegal. Now, one of my contributions was to make a very efficient encoding of these border states. Let's say we have this state where these stones are all without liberties, but one is somehow connected to this one. These pipes are connected, could be a black stone here, and also this white stone is connected with this. Note that due to planarity constraints, these connections cannot go across each other. That allows us to represent these connections with just arrows, left and right. So if we know that this has some connection to the right, and this stone has some connection to the right, this has gone to the left, okay, then these must match up. And these must match up, and these must go all the way around it. So from just knowing that there are some left or right connections, we can infer all the connections. Note also that these stones are gray. We don't need to know whether they are white or black, because color can be inferred as well by looking at the neighbor. This is a black stone with liberties, so then we know that this must be a libertyless white stone. If it were black, it would share its liberties with this stone. And we can infer all these colors similarly. Border states will also include a notion of color symmetry, so if we swap all the blacks and all the whites, then we know this position should have the same count. In total, we only need 3 bits per point to encode all the necessary information about a border state. So it's essentially about a partial position, which is nice because with 19 points across, we only need 57 bits, which again fits neatly into a machine word. However, there are a lot of possible border states. If you count them exactly, it's over 363 billion. Now each of these state and count can be represented in 64 bits, so that's 16 bytes per pair. But with this many border states, we're looking at 5.8 terabytes for just encoding counts of partial board positions. Yes?
2 minutes.
2 minutes. Ouch. Okay, so let's move on. There's some redundancy still. We need 4 terabytes on disk. And if we look at the distribution of these states in the code space, so this is the space of encodings, it's very non-uniform. So it's actually tricky to partition it across multiple CPUs. Here is the official representation of the main algorithm. We have such a data set on disk, a total of 4 terabytes. We're going to use 4 CPUs to process it. So each CPU takes care of a particular range of encodings. And these files all have the states sorted, so it can read them all simultaneously, basically merge all these streams of states. Sometimes you see a state occurring in, multiple times, so then you just have to combine it by adding the counts. Then you generate the possible successors of this state by considering the next point to be empty, white, or black. And you dump these new states into memory. When the memory fills up, then you again figure out, okay, which part should go to CPU 0, CPU 1, CPU 2, and 3. So you dump these files, sorted files in here. And then you have the partial counts for the next partial board size. You repeat this whole process 361 times, and then you'll have finally the counts for the complete board. And you just extract the ones that correspond to completely legal states, so no more libertyless stuff. Software is available. You can run this yourself if you have a beefy server machine and pick a new random modulus and check that the results match. There's some built-in error checking on all the files, several other properties that have to be satisfied. But like I said, the main check is that the result that we get after doing the Chinese remainder theorem, does it match what we predicted it would be? And yes, it matches in the first 10 digits, so that gives a lot of confidence. Concluding remarks. So dynamic programming allowed us to reduce a problem that's exponential in n squared, brute force counting, which is completely impossible. You cannot count one by one up to 10 to the 170. To a problem that's exponential in only n, which is just barely feasible. we answered the ultimate question of liberty is the universe and every string. Using these last two values of 19 by 19 and 18 by 18, and also the not quite square board 19 by 18, we can improve our good old approximation formula. That for any m by n board, the number of positions is approximately this. And actually all of these digits are relevant. Can be expected to be correct. Of course, this is still an approximation, but the error will be very small. Also, Go counting makes a very nice server benchmark. Let's skip the details of that. Finally, now that we have computed positions in the king of games, Go, I can move on to considering the game of kings. But that will be much more troublesome. As this position shows, it is hard to even determine a position where it will be very hard to determine if this can be reached by a legal sequence of moves. Okay, any more questions?
That you just showed, is there proof that certain constants exist where that's always exact?
What you can show is that if you take normal legal m by n positions and you take the m times n root of that, then it converges to a constant of which we know
Any
by the
proof
first.
about whether or not that constant is rational? Or
No idea. It's expected to be irrational.
I assume the calculation is including symmetries, right?
No.
Oh, it does. So
No.
this is
Most boards will be counted 8 times.
that's what
Actually
I
16 times if you also include color symmetry.
Oh.
Yeah.
How difficult would it be?
Sorry, questions can be taken offline.